Last time we talked about bridging, which is an advanced, more advanced device than hub and the T connector, right? So because it can separate, the channels a little bit. You don't broadcast everything to everyone, okay? And we talked about that bridge, right? So each port is connected to a LAN, right? Local area network. And an extreme case is Ethernet switch, which is quite popular these days, and probably most of the architecture are using the Ethernet switch. Okay, and in that extreme case, each local area network is actually one host. Okay, so every host, as long as you are not talking to the same person, right? If both of you are sending a movie to the same receiver, right, and each will share the receiver side half the bandwidth. Otherwise, you can send in full speed if there's no conflict. Okay, and other people will not hear what you say in some sense. Okay. And last time we talked about how this bridge will auto configure itself, right, to learn where the port is. Okay, it has a routing table where it will basically whenever the port receives some host Ethernet frame, it will have the source MAC address, right, and it will record that and along with the port number. Okay, so it knows when it is connected. And we do have to have an age information because once it's timeout, right, we want to forget it. And if you keep sending stuff, right, so the age will be reset to 0 constantly. So it's very unlikely your item will be removed, okay, unless you set idle for a long period of time. But on the other hand, so if you get removed, right, this timeout mechanism will allow timely removal of these hosts that are disconnected from your Ethernet, okay, from your your subnet. And last time we see how things works when there's no cycles, right? But when there's a cycle, what will happen here? Here, let's go back to this example as a recap. Okay, so let's assume that AA. I'm not sure whether you can see it clearly. So AA is this machine. This is AA. Okay, and you want to send to DD from AA to DD. Okay, and in order to do that, what you will do is you will send assume that there's empty routing table initially. Okay, then you will send AA, a frame with source being AA, this frame, right, to both, to both port 1 of both bridge. Okay, and the bridge will forward to port 2, right? Actually, it will broadcast to port 2 because it has no information about DD, so it will broadcast. Okay, and once it put on this wall, right, so the hub is like a shared media, it will reach the other bridge. Okay, and similarly, this will reach you. Right? And even though DD successfully received your packet, okay, but if DD never sent anything to respond, by that time, these devices will not know that DD has received it anyway, right? So, so it will not terminate because this time, this packet comes to this bridge here from port 2 instead of port 1. So this will be updating to port 2. Okay, and then it will, because it's coming from port 2, and there's no destination DD yet because DD had not sent anything. Okay, then it will be forwarded to, the other side, and go to port 1, and then change it to port 1 and repeat. Okay. So simply, if you have a cycle, maybe it will flow, it will never end. Okay. So that's not good. Like in this toy example, in general, if you have a cycle, you will have this kind of damage. In this toy example, we only have one cycle. It's totally just a cycle, right? So this will just alternate from port 1, port 2, port 1, port 2 forever, unless sometimes, let's say, DD sends something, right? If DD sends something, then DD is on port 2, you will not send back to port 1 anymore. Okay. All right. So how do we stop this kind of infinite loop, right? We want to remove the loop, right? Maybe we don't send anything through this link, right? And you stop right here. You don't go to the other side. Okay? So we need to remove the loop from the topology, but we don't physically unplug those cables, right? people can just configure everything, right? But we will logically assume this link will never be used. Okay? So we are using a algorithm that maintains a spanning tree of the routers, okay? Routing those hub and the bridge, okay? And find the host, okay? So how do we achieve that? So here's the example where we have, here it's an abstract the previous structure into a graph, okay, where if two hosts are connected, or two like a bridge, or its devices are connected, you have that. Okay, and so you can see there are a lot of cycles, right? This is cycle, this is cycle, and 1, 2, 5, 6, 4 is another cycle, right? And then 1, 2, 3, 7, 6, 4 is another cycle. There's many cycles. Okay, and so how do we avoid those cycles? Well, you can create a spanning tree. Okay, let's say starting from 5, starting from 1, we have 2, right? But we send to 4, and then send to 5, and then send to 2, and 6, and then reach 3. Right? If we do something like this, then this is a tree, and the 3 will reach that. Okay, not reach. And this will structure the tree, and it will be something like this. Right? 5 is the root. Right? You can, because if 5 is the root, you minimize the diameter, right? At most. If you make a 1, it can go quite long. 1, 4, 5, 2, 3, 7. It's much longer. Okay. So if we put the center node 5 as a root, okay, as a tree, and then you can see these are the tree edges. 5, 4, 1 is this tree. Okay. So as a summary for this 802.1 spanning tree approach, right? So what we are doing is we elect the bridge to be the root of the tree. Let's say it's a 5. Okay, you can randomly, like everyone, just elect and find the one with the smallest MAC address, okay, or with the smallest I think that's one solution. Okay, you can have another way, okay, like diameter, but that need a lot more communication, right? And once you elect the root of the tree, what you can do is every bridge will find a short path to the root, right? Because if you look at here, once we decide, hey, 5 is a root, okay, everyone can find its shorter path. Right? 6 to 5 is just one edge. Okay? And 7, this is not in the tree, so you go to 3, go to 2, go to 5. Okay, so you look at this. Somehow I see some information like my internet is unstable. I just want to make sure everyone can hear me. So still. Okay, if you cannot hear me, just let me know. Okay. Okay. Is it better now? Is it better now?
Yeah, it sounds better.
Okay, audio is better now, right? So I hope things get better. Okay, so yeah, I see one message from Jackson says audio is better, so let's continue. Okay, if it's not working well, just let me know. Okay, yeah, let's continue. So first we will determine a root, right? Let's say the device with the smallest ID, and then everyone will know its unique path to the root. Okay, and then union of those paths gives you the spanning tree. So this is basically also the algorithm in substances. Okay, so in order to do that, so actually the bridges themselves, right, need to exchange something. Okay, these nodes, right, need to exchange so-called configuration bridge protocol, so-called BPDUs, okay, called bridge protocol data units. Okay, so this BPDUs are for configuration. Okay, so bridges will exchange configuration BPDUs to build a tree. Okay, these are just bringing the bridges, okay, to decide, hey, what are the tree edges between every two bridge. They're not forwarding the host packet frame. Okay, So that's only for configuration of the tree, spanning tree. So this is the BPDU. This protocol is used to elect the root bridge and calculate the shortest path, right, where to go to the root, and locate the next hop to the root, right? So, and its port, for example, if you look at here, right? For example, if you think about this, 1 will go to 5, right? But maybe 4 has 3 ports, 1, 2, 3, okay? Right. So you should say, hey, I should go to, when I want to go to 5, the next hop is 4, right? Frankly speaking, you need to go to everyone by first sending things to 4. That's the purpose. It's a tree. You cannot go to 6 or 2, okay? And then once it's there, you need to send along port 2 or 4. Okay? So that's basically the concept here. Locate the next hop closest to the root and its port, okay? And you will select ports to be included in the spanning tree, right? So which port you want to include in spanning. Basically, you know. So like for 4, maybe these 2 ports for the 4, not 4, bridge 4 is in the spanning tree, but this one to 6 is not in the spanning tree, okay? So, but one important thing is that, you know, these bridges are totally, you know, initially they're isolated, right? You don't want to configure them manually, because they will exchange these BPDUs, okay, to configure them themselves, right? How to achieve these steps? What should be the structure, the protocol format, right, for the what to transmit between these bridges? Okay, that's what we are talking about. So, firstly, every bridge will have a random number, okay, so that the probability that they conflict very low, right? So it's a bridge ID, okay, and you can think everyone has a unique ID, right? And then the root bridge is really the bridge with the lowest ID, okay? So why we need this? Because when you receive other people, you know, BPDUs, right? BPDU will contain this ID, right? Then you know whether the other people should be the root instead of you, okay? So this is, you know, using the BID, you can elect the root. There's also a pass cost, right? What is the pass cost? It's the cost in terms of number of hops. Okay, maybe some different hops will have some different propagation delay, but we don't count them. Okay, we really just simply count how many hops it takes to the root. Okay, the cost from transmitting bridge to the root. For example, if you go back to the previous tree, I think we have
okay.
Yeah, any question? I see a message. Okay, so I got a message that audio is breaking up. Can you hear me clearly? Okay, I see a student confirm. So for example, from 1 to 5, the root, right? There are 2 hops, okay? And 7 there are 3 hops. Okay? From 3 to 5, there are 2 hops, okay? So that's the hop information here. Let me see which slide we should. And this is a pass cost, which is measured in the number of hops, okay? And each port on the bridge has a unique port ID, right? So 1, 2, 3, like each, no, each bridge has multiple ports, okay? Oh, I don't know what happened. So maybe just a moment. Let me see whether. Yeah, I don't know because maybe my Wi-Fi is not good right now. So I will share the video. Okay, you can rewatch the video if the quality is really low. Hopefully that will address the concern. Next time I will double check whether my connection bad and see whether there will be a solution. And so the root port, the port that goes to the root on each bridge. Okay. So basically, I don't want to go back to the previous slide. So basically, you have 5, right? Let's say you have 5, you have maybe 4 and 1, right? And maybe 1 also connect to something else, but they are not part of the tree, right? So maybe the 1 has 3 ports. Okay. So this is the root port, right? This port is the root port. The others are not root port. So this is the concept. what is the root port. Okay. So the designate bridge is the bridge on a LAN that provides a minimal cost path to the root, right? So this is really, you know, the designate bridges. So it's basically the parent in the tree, okay? So so of course, if you are connected, so you know, because it's a tree, so if you are in the tree, you can only go all the way to the root, right? So for example, if you are 1, right, you will not send to 2 because it's not part of the tree, right? So that's in the bridge, right? So 1, go 4, go 5. It's unique, right? If you want to go to 2, it should be 1, 4, 5, 2, right? It's a minimum cost. Okay? But we want to find the minimum spanning tree, which means, you know, we want to as small number of hops as possible. Okay. So that's what we say the minimal cost path, right? So because cost path is the number of hops. If we can reach the routing 2 hops, we don't want to go another path which takes 3 hops. Okay, that's the idea. So to determine the root, initially all hosts will assume their root, right? And then because you only see your ID, of course the ID is the smallest. Then bridges will broadcast the BDUs, okay? And it contains 3 fields. The first is the root ID, my root ID, right? The second is my cost to root. If initially the path cost is 0, right? It's 0 hop to myself, okay? And then we'll have a bridge ID, which is my current bridge ID. Okay? And then they will send to each other, and you will repeatedly receive, because you know broadcast means it's not just sent to its neighbors. The neighbor will forward them, right, until everyone is reached. Okay, so then at the end, everyone will see everyone else root ID. Then they will know who has the smallest ID, and they will have a consistent, you know, conclusion who is the root. Okay. So based on the received BDUs, of course, each one can only send to its neighbors that are directly linked, right? Then each switch will choose a new root, right? Because it's the smallest, right? You see so far, okay? And if this can change still, right? Because maybe 2 hops away sent to me, and 3 hops away sent to me, maybe I will see a smaller one, okay? And then we'll choose a new root port, right? So which interface goes towards the root, right? So it's basically the next bridge on the tree edge, okay? Going out of my current bridge, right? And a new designated bridge, right? So who is the next hop to send to? I think it's still helpful if you go to the tree structure. Maybe let me just plot it. Okay, so let's say you have a tree, something like this, right? And you have 1 hop and you have 3 hops. Okay? And here, for example, a new root, right? Whenever you see a small ID, like this is 1, this is 4, then I think a 1 is the root, right? Next time maybe a 0 comes, then I know 0 is the root. Okay, so this depends on when this package root is broadcast to you, right? It's a broadcast. Okay. Now, whenever you see an update, that's a new 0 comes, then you say, hey, now the new root is 0, right? The port is still going through 1, okay, then to 0. Okay, and the new designated bridge, right? Who is my next hop, right? This is 1. Okay, I had to go to 1 to go to 0, right? And you can see that you know, there's a possibility, let's say, because there could be cycles in the physical architecture. I can also go this way. Right? I don't have to go through 1 to 0. I can go through maybe 2 to 0, okay, 3 to 0. Right? And this, again, this could be equal because they are both 2 hops, but there could be a even worse path, like 2, 3, 0. Okay, and then we should really go. The next hop should be 1 instead of 2, right? So that's how the protocol will also handle that, right? We want to get a path cost to root, and we'll always choose, you know, my neighbor bridge, which has a smaller cost to root. Okay, so here's an example, right? Let's say this is a current bridge. Okay, this is an upstream bridge, which is sending stuff to me, right? And who should be my next hop to the root, right? I should choose one of them, okay? So firstly, you know, if the root ID is smaller than R2, then we will always choose R1. The reason very simple. R2 is a kind of behind the schedule, right? So maybe R1 is this smaller ID zeros, bridge zeros broadcast message have not reached there, right? I should ignore this one. This one is totally outdated, okay? So this is this line, what it means. And if they are on the same page, let's say both upstream bridges, okay? They basically see the same route, okay? This is what happened, okay? And then we can talk about the cost, right? Who is shorter to that route, okay? And of course, we prefer a shorter one, right? If cost 1 is shorter, like this can reach the new route in 2 hops, but this needs 3 hops. I will choose this one as my next hop bridge, okay? I will choose this one. If they're equal, then what I can do is I will have the bridge ID to break the tie, okay? The bridge ID is really, random number, right? And remember, this R1, R2 are also bridge ID, right? But this is root bridge ID, so that's why R is root, okay? This B means bridge, right? But it's really the next hops bridge, right? So the upstream, bridge who sends these BPDUs to me, okay? And I will just break tie of whoever has a smaller ID, I will take it, right? So back to previous example, if we have the root 1 and we go, right, both are 2 hops, okay, to me. I will see which one has a smaller ID, okay? But this basically say if this is 2, this is 3, I will choose 2 to be my next hop bridge, okay? And so you see, if I'm so if this bridge is shorter, I will choose this one. If they are equally, like if both are 2 hops, I will still choose B1 if B1 has a smaller bridge ID. Okay. And finally, if all these doesn't hold, I will choose B2. Okay. Now, it could be that cost 1 is larger than cost 2. Cost 2 is better. Okay. Or the bridge ID of B2 is better. Okay. So you can see by this way and by the broadcast, right? Everyone's broadcasting this, and until this packet reach everyone else, okay? And then, of course, you need to add the cost whenever you broadcast this message to the next hop, okay? But by everyone, when they all reach this, you can easily see that the tree shape is uniquely defined, right? Because if you're given, let me give you, so firstly, you know that because this rule, the smallest ID bridge will be the root, okay? And then you know that, the cost is uniquely defined, right? And the ID is uniquely defined. Then every edge to the root is uniquely defined, okay? So by running this BPDU messages, okay, finally everyone will determine its next hop bridge to the root, okay? And then along the route will pass messages with other, bridges, among other bridges. And that will be unique, right? So there's only a unique path between every people. Okay? So here you can see these are what I explained, right? This is saying that R2 has not seen the true route yet, right? A better route yet, okay? If they both see the better route, we will choose a closer path, okay? And if both are the same, again, then we have to break the tie by the bridge ID. So what's the difference between bridge and switch, right? So both bridge and switch can separate, the channels, right? So basically, if A is talking to B, C and D, they will not hear them, right? So C and D can send to each other simultaneously. Okay, this is not the case in hub, right? But bridge is really connecting lanes, right? So it's making it possible to increase LAN capacity, because if you are just talking to each other in the same LAN, you will not send stuff to other LANs. Okay, if you are just talking from A's LAN to B's LAN, then C and D's LAN, if they are in different LANs, they will not be hearing those things. So they can keep communicating. And this will reduce the amount of broadcast packets, right? So the reason is very simple, right? So your broadcast only happens within your LAN. Okay, if your broadcast within the LAN, you don't need to reach people outside, right? So you can stop there, right? The bridge will separate them. Okay, and there's no loop, right? Because we will elect a spanning tree and let it function as a path to propagate the packets. Yes. So switch is a special case of bridge. Okay, where each port is connected to a single host instead of a LAN, right? And it can either be a client machine or it can be another switch, right? So you can make it a hierarchical structure, which is actually now people don't use bridge anymore. Okay, everyone's using switch. Okay, so this is the concept, right? You have a switch, right? These are hosts. Okay, these are hosts. But now there are too many hosts here. Okay, but you need to be bigger, right? You can even this port you can connect to another switch and then connect a bunch more machines. Right? Another common architecture is these are all like this is a tier 1 switch, this is a tier 2 switch, and then connect hosts. Okay, this will allow you to connect a lot of hosts in your subnetwork. So so links are 4 duplex, which means if you send A to send to B in 1 Gbps, B can also send to A in 1 Gbps. Okay, this simplifies hardware, right? So there's no need for this kind of shared media control like CSMA CD. Okay, and so can have different speeds on each port. Right? So really important because if you're, let's say you have a 10 Gbps switch, but it's connected to a 1 Gbps switch in the next layer, right? So they can still, so on this port maybe you send 1 Gbps, right? And here maybe a lot of them are coming upstairs and want to reach the other subnet LAN here. Okay, then you can use 10 Gbps, right, on this link. Okay, so this port can be 10 Gbps, but this port can be just 1 Gbps. Right? And yeah, if you have any question, feel free to ask me. Okay. So another question is, now we know that switch, right? We have a switch. It seems that it's pretty nice already. Right? Why do we like IP address? We have the network layer. This is the link layer, right? I just switch every computer in the world, right? So into one like a subnet, right? So that seems functioning, right? But this is not practical. Okay. So the capabilities of switches are as follows. Right? So this is a network-wide routing based on the MAC address, and learn the routes to new hosts automatically. Right? You know which host is on which port, and you will resolve loops. Right? You will decide which links should be passing. Right? So spanning tree links. Right? But we cannot really use it for the whole internet. Okay. The answer is really no. The reason is that it's very inefficient. If you remember, if we have a new host joining, right? Let's say you set up a new server in the internet with a new website, right? So in that case, people don't know you initially, right? Say if you are communicating, and so what can happen is that you have to flood the packets to everyone. This we'll see if somebody new join, okay, initially. And in that case, because you don't know which host is connected to which port, right, you have to flood to everyone together. Okay? This flooding packet operation, right, to locate an unknown host is very inefficient when it scales up. Okay? If you have 10 machines, that's fine. Right? Everyone, if you have 1 billion, everyone is sending to another 1 billion, broadcasting to everyone. Right? That will never end. Okay? So the performance could be very poor. And another problem is that the spanning tree does not balance load, right? So you can see our previous spanning tree is something like this. So you have 2 links here, 1 link here, 3 links here, okay? And this is actually connected dynamically, right? So maybe next time it will build up here. Okay, so gradually this tree is not balanced. Okay, so maybe some branch will have a lot of cost. Okay, this is not a problem actually in your Ethernet. It's a small scale, maybe 3 or 4 hops are fine, right? But if you think about 1,000 hops, that will delay everything, okay? And that could be hotspots where it causes a lot of congestion. Okay? So this is really for a small scale local subnetwork. Okay, you cannot use it for the internet. So we also need the network layer. Okay. Another problem is that the scalability is poor, is because each switch needs a unique MAC address, right? But that's fine. This is also what happens now. but these MAC addresses need to be in the routing table. Okay, so we will see in the next lecture that the the routing table in the bridge or in the switch is totally different from the routing table in the routers in the network layer. Because in the routers, you don't want to, let's say you have 1 billion, okay, you have 1 billion computers connected, right? If it's connect to your subnetwork, you need to have 1 billion entries. Each has its MAC address and the port number. Okay, that's kind of too big for the hardware. Okay, but for routers, usually this will be a IP address group. Okay, so you have a prefix. You can group what's it afterwards, and you can delegate the routing of those to the next hop router. Okay? So you can control the routing table size to be manageable by the router, by the hardware device. Okay? But we'll see that later. But essentially, so this data link layer solution for the routing is only suitable for maybe hundreds of machines locally. Okay? It's really not for 1 billion machines. So IP address will be solving this problem. Okay. So let's go to the next slide. So then we will move to the network layer, and we will have 2 slides. After these 2 slides, we will have the midterm. Okay. And it will be a timed quiz kind of form. Okay. And it will have more questions. It will be in class though, so it will be 50 minutes. Okay, so we will not ask you too difficult questions. Okay, but be sure to familiarize yourself with all the previous quizzes, because it's time. Okay, and so it will be a short one, right? So the final exam will be a relatively longer one. Okay, midterm will just test your understanding so far. And let's then move to the networking layer. Right? So because previously we are talking about the data link layer, now we're at the network layer. Well, we really address the problem. The routing table is too big if we use that for the full internet. Okay? So the midterm will be, I don't know when I can finish these 2 slides, but I think next week we probably will not have the midterm. The week after we will have. Probably by next Friday, I will go over what we will test you on the midterm. Okay, then you can prepare for it. Okay. It's quiz based, but it's timed. Okay, so your quiz is not timed, right? You can take maybe 1 day to finish that. It's fine. Right? So we are not really deducting your mark for taking a lot of time, but midterm will be timed. Okay, and in class. But it's a quiz. You still log on cameras, but we will time it, and the time period will be that period in the class. So how many questions? We will have probably 20 to 30 questions, okay? In between 20 and 30. But it will be something similar to what we have here. It's like 2 to 3 minutes per question, right? So I think, yeah, so 2 minutes per question, kind of. It will, yeah, there's a question whether it will be based on quiz. It will be very similar to the quiz. I cannot say it will be exactly the same. And we will also go through some additional stuff to highlight what we might test you, okay? If, maybe next Friday, okay? So you don't have to worry too much, okay? Of course, we will not choose exactly the same numbers, right? So if we use the same numbers, and you can copy from the quiz. We will do some changes, right? So, but it will be basically the same range, and we will have before the midterm exam, we will have a lecture, go through what we might test you. Okay. All right, let's begin. Okay. So we have 2 lectures for 2 slides for this network layer. Okay. So in the network layer, so what's the function of the network layer? Just a recap, because we have seen that in the very beginning, right? So the network layer routes packets end to end on the network, right? So it's not just in your subnet, right? So it's routing from one subnet to the other subnet, okay? Multiple hops. It could be typically 10 hops, even more, right? And you can use a trace route to see these the routers along the path. And the key challenges here is actually how to represent the address, right? Now we cannot just use the MAC address as random and everyone is unique and there's no hierarchical structure. IP address has a hierarchical structure, okay, locality shape, right? Like if you are in Birmingham, it always starts from this segment of IP, right? So the prefix is the same. We will see that shortly, okay? And UAB may be the first 2 bytes, I would say. And how to route packets, right? It should be scalable, right? And it should converge, right? So you cannot this time take this route, that time take that route, okay? And so there will be some protocol like a BGP protocol. Okay, we'll see those things later. There's some like a shortest path computation, right? Just like in the previous one, right? So the data link layer, the bridge we use the hops, okay? But for the network layer, really hops is not enough, right? We care about the latency, okay? All right, let's revisit. Okay, so what is a router? Okay, so router is connecting, multiple lanes. Okay, and so previously we are within this lane. We see those bridges. Okay, and this lane can be Ethernet. You can have a Wi-Fi, right? You have the wireless router connect to the one port of the bridge or switch. Okay, and so the routers are actually these devices, right? It will connect those subnets, okay, so that you can send a packet to another subnet. And so connected network is called internet, right? So internet is just an example of internet, right? Because it's like the backbone. Everyone's connected there. As long as you have an access point, you are there. Okay? Maybe you are in a favorable corner of the internet, and it takes a little bit longer latency, but anyway, you can reach everyone. Okay. So the structure of the internet, right? So is here you have internally those switches. We are ignoring them, right? But you have the those router coming out, okay? And then you can connect everyone to everyone else, right? So this is how do we structure them? Right? So we have an ad hoc interconnection, right? So you don't need to manually specify them. Right? So there's no organized topology, right? And they can depend on very different technologies in the link capacities, right? So these can be very different router devices, okay? And maybe the different ISPs have different routers, okay? So it can be very diversified devices. And the packets travel end to end by hopping through a network, which means, for example, you have a host here, and you have a host here, right? It travels end to end, okay? Above the network layer, you don't care about what's happening in the middle. Okay? The routing is fully handled in the network layer. Okay? After that, you just think about the host, sending host and receiving host, what happened here. Okay? And so the routers like this, like peers, right? They help each other, okay? Connect different networks, and different packets may take different routes. Okay? So these, these routers should be run a lot of time either by UAB, right? UAB has an internal router, and there's a portal one, right? So and then it goes out, right? And then you have so-called internet service provider, right? Otherwise, there's no motivation to pay the router, right? So you want to be connected, you pay them, they build the backbone routers for you. Right. So here, for example, you can have a host in the red network and send a packet to the one in the blue network. Okay, another host. Right. So this end to end, but you can take a different route. Right. You can either go through the purple, intermediate network, or you can go through the green one. Right. So which one you should go? And this is actually we have the protocol. But maybe sometimes a lot of people are sending packet between network 1 and network 3, and this is too busy, then maybe it will be rerouted through network 2. Okay, we will see something later. And so you can also have asymmetric traffic, right? So because it's fully duplicate, right? So you can send through, 1, 3, 4, but when the other host send it back, it can go through 4, 3, 2, 1, right? So it doesn't have to use a 3-1 this thing, right? This can happen, right? So because, for example, if there's a lot of people sending stuff from here to here, from network 3 to network 1, if you have to, let me change it cooler. If you don't go this way, you have to go this way, then you are competing the bandwidth, right? Maybe there's too long latency, so the router will have a mechanism to say, hey, this is faster. So the back route may not be the same as the route that you count. Okay. So there are a few issues with internet networking. Okay. One is like a naming and address, right? How do you designate host, right? Previously we said we have the MAC address, right? And here we know that we have the IP address. I will heard of it, right? So, but how do we give the address for each host? Right? And then another important question is how to do routing, because previously we say that for your whole subnet, each host should have a unique MAC address, right? But you cannot scale this to the whole internet because there are too many items in the routing table. Right? The hardware can only support a limited number of routing table, okay? Routing table entries. Okay? If you have a billion entries there, the device will never work. Okay? So router is the same, right? So how can we make it scalable, right? A switch the internet won't work. Okay? So we will see that the IP address is designed to be scalable. Okay? There's a prefix, group by prefix, basically. Okay? And there's also what service model is adopted, right? What gets sent and how fast it will go, right? And what happens if there are failures, okay? Right, so maybe some route in the middle suddenly disconnect, then how do you handle that, right? And you also need to deal with heterogeneity, right? Because different networks is totally different, and even hardware is different. Okay, so the internet service model actually is what we call the best effort one. Things may break. There's no guarantee. Okay? If things breaks, then you retransmit or you find another route. Okay, and for each router, it's very simple, and we discussed that very early. Right? So it will, when it comes gets something from incoming port, it will just store it if there's a buffer, right, and then forward it to the outgoing port. Okay, so this is the router is just doing this simple stuff. It will look up to your IP address and decide which port to go to, but basically it's just doing this, right? No more than this. Okay? And it's really doing so-called the lowest common denominator, which means if you have ABCs, the other guy has BCDs, then it just implement BC. Okay? It doesn't implement anything beyond. So possible addressing schemes, as we said, the IP address is carefully designed to be flat, right? Because the MAC address is flat. Okay, it's a 48-bit MAC address, and so it's totally flat. Each one has a unique address, right? And router, if we use this flat design, router need an entry for every host in the world, right? So this is not gonna scale too big and hard to maintain, right? Because some hosts may be down, right? So we cannot just use a subnet solution for the whole internet. Okay? So we will use a hierarchical structure, right? We build a hierarchy, and the addresses are broken down into segments. Okay, and there are 4 segments in IP address, right? And the prefix decides where you are in different units, right? And each segment will have a different level of specificity. Okay. This is quite similar to the phone number, right? So this is the United States, the first one, and the 205 means Alabama, right? And you have this may be a Jefferson County, right? The county, okay? And finally, the 4-digit may be which location it is, right? The IP address is following similar design. I think we'll continue next time. Let's take attendance. Okay. So the IP address will follow a various similar design. We will continue next time from this slide.